contemporary kung fu practitioners, the existence of qi has never been under question. When properly focused, this is the energy that enables them to transcend the physical limitations of flesh and blood and perform feats that appear to challenge the impossible.
All right, so I've seen martial artists break one, possibly two bricks at a time. I've never seen what he's about to do. Never seen this before. All right, so obviously he broke the first one. Second one is broken. The third one is broken. The fourth one is broken. All right. So my question to you is the fact that this guy was able to break 4 bricks with a single strike. Does this make him stronger or more powerful than his counterpart, who's going to be able to break only 1 brick at a time? What do you think? Does he need to be stronger or more powerful than his counterpart who can only break 1 brick at a time? All right, guys, most of you guys are thinking I'm asking the same question twice. No, I'm not. All right, so what we're doing is we're doing a comparison. Imagine that this guy is able to break 4 bricks at a time, and his counterpart is able to break only 1 brick at a time. So the fact that this guy can break 4 bricks at a time, does that make him stronger or more powerful? What do you think? It gets confusing.
So power is the ability to do work quicker.
Okay, very good. All right, you got a good start. Okay, so I'm going to give you 10 points because all of a sudden you're thinking, wait a minute. I mean, he could be stronger and more powerful, right? At the same time. I mean, the guy who's stronger, by definition, is probably more powerful, whatever that means. Okay, so let's think. But is it possible that they could be just as strong as the other one is more powerful? Okay, so that's what I'm trying to put the emphasis on. All right, so imagine that we got 2 martial artists. They're equally strong. How do we know that? Because they're going to be able to lift the same maximum amount of weights. Both of them are going to be able to lift or bench press, say, about 300 pounds and not a pound more. Okay, so let's imagine that that's the strength, that's the measure of strength in both cases. Except one of them is going to be able to break 4 bricks at a time. The other guy is only going to be able to break 1 brick at a time. All right, so the guy who's breaking 4 bricks at a time is got to be more powerful because what is power, guys? The power is how fast the work is done, right? But what is work in this case? The work is force causing displacement, force causing deformation. All right, so which means that the guy, how fast the work is done, how fast the energy is transferred. In this case, the energy is being transferred in the form of deforming something, breaking something. The guy who's breaking 4 bricks at a time is more powerful because that's what he does. He's causing a lot more displacement than the guy who's breaking 1 brick at a time. Okay, another expression of power is how fast the force is transferred, guys. Remember, both of these guys are equally strong, except one is able to break 4 bricks at a time. This guy.
The computer displays the results. First,
versus a novice.
The novice.
Imagine that this guy is just as strong as the novices. Okay, so they're going to be able to lift this or bench press the same amount of weight. That's what it means. That when the novice hits the brick, this is what you end up getting. The duration is much longer. And when an expert hits it, the duration is much smaller. Why? Because more powerful individual is going to be able to move that force at a much greater speed. All right.
The difference is the enormous speed of his hand, compressed into a short space of time.
These experts are moving their hands much faster. Believe it or not, guys, I can move my hand just as fast, so can you. There's nothing special about this guy. He's got the technique. You can master the technique within 5 minutes. All right. This guy is going to be able to break, say, about 4 bricks at a time, and you won't be able to break more than 1 if you're lucky. All right. So why? What makes him more powerful than you? You're just as strong as he is. You can move your hand just as fast, except this guy is highly practiced. There's no hesitation there. There's absolutely no hesitation there. He knows he's going to be able to break it. If I've never done it before, I'm just going to chicken out in the last second because I don't want to hurt myself. I don't want to break my hand. All right. So you're not going to go as fast. There's going to be hesitation. So that's
experts can perform extraordinarily impressive feats, but it takes a great deal of special training.
All right. So next question is the impulse generated. The amount of impulse generated when you break through the target versus you hit it really hard, but it doesn't break. Okay. So which impulse is going to be larger? The impulse generated when you break through something, whenever you're breaking a surface like that, or impulse generated, you hit it really hard, but it doesn't break. Which impulse is going to be large? Which change of momentum is going to be large? All right, guys.
Would it be when it doesn't break?
when it doesn't break. Absolutely, because you go in, you're trying to break the tabletop, you're going in really, really fast, say about 40 miles per hour. You go from 40 to 0. So that's your impulse, right? Change in momentum. Okay, when you break through the surface, what happens? Your hand does not stop. Change in momentum is very small under the circumstances. Change in momentum is very small, and the duration of the impact is extremely small. You generate duration of the impact is going to be 10th of a second, 100th of a second, which means that the amount of force that you're applying becomes much, much larger under the circumstances. And when you hit, and if you're not breaking the surface, duration of impact is much longer. The amount of force you're applying is not as large. All right. So regardless, though, the amount of force that you're applying on a surface is going to be the same amount of force that the surface is going to apply back on you, right? So that's the action and reaction law. All right, guys, put your answers in there in the chat. Okay, this one is going to be easy. All right, so the best answer is going to be, it's going to be C, right? The action and reaction forces are the same. All right, so action and reaction forces will be the same. So they will be identical to each other. C is the best answer. All right, so action and reaction forces will be the same. Head-on collision between two masses. Which one is going to experience a larger impact force? Same question. Head-on collision between a car and an SUV. Which one experiences a larger impact force? Same question. The person getting hit by a train. Which one experiences a larger impact force? It's always the same. Action and reaction law. All right, so in impact collisions, action and reaction forces will always be the same. Newton's third law. All right, so this is going to take us into a powerful concept. All right, guys, we're still doing a review. Otherwise known as the conservation of momentum. So that's what we're going to be dealing with. So head-on collision between two masses. Action forces acting on mass 2, reaction forces acting on mass number 1. We're going to be looking at the impulses on these two masses. The first one is mass number 1, reaction forces acting on mass number 1 for this duration. So what it does is going to change the motion of mass number 1. So the velocity is going to change. Second impulse is acting on the mass number 2. So action force is acting on the mass number 2 for this duration. So what happens is the velocity of mass 2 is going to change. Now let's take a look at the total impulse of the system. When we say system, guys, the system is a system that only concerns itself with the colliding objects. All right. So in this case, our system is going to be composed of mass 1 and mass number 2. So we're looking at the total impulse of the system. All right. So total impulse of the system is this plus that. So the reaction force acting on mass number 1 plus the action force acting on mass number 2, duration is going to be the same for this duration. All right, so they're going to have the same impact on them. That's what it means. So what happens during the impulse is the momentum of the first mass is going to change, and then the momentum of the second mass is going to change. So the motion of the first mass changes, the motion of the second mass changes. That's what happens during impulse. All right, impulse formula came out of Newton's second law, which is force causing acceleration or force causing acceleration. What causes acceleration is a net external force. All right, so the force has to be the net force, so that's the total force. And it needs to be an external force. Yeah. So this is the net force acting on the system. That's going to be causing the acceleration of the system. Once again, guys, the system is composed of colliding masses here. It could be colliding objects, the masses, the particles, or whatnot. So what is the net force of the system? So we're not talking about the net force of the individual masses. We're talking about the net force of a system. So we're summing up the forces. Notice that this one is a reaction force, this one is an action force. So you got the action and reaction forces. They will be equal to each other, and they will be in opposite directions. All right, so the action and reaction forces will be equal to each other. They will be in opposite directions because of the third law. All right, so the back substitution. Add up to 0. So the net force acting on a system is 0, which means that the impulse of a system is going to be 0. All right, so what is that supposed to mean? All right, so what that means is the total change in momentum of the system is going to be 0. So here's the change in momentum of the first mass. Here's the change in momentum of the second mass. The momentum of this first change in momentum of the first mass is going to be the same as the change in momentum of the second mass. That's what it means. All right. So however much the motion changes for the first mass is going to change the same amount for the second mass. All right. I'll keep final velocities for each mass on the left-hand side, initial velocities for each mass on the right-hand side. This will represent final momentum of the system, and this will represent the initial momentum of the system. Notice that the final momentum of the system is the same as the initial momentum of a system. So which means that in collisions, the momentum is going to remain constant, which means that every single collision is going to conserve momentum. That's what it means. Stuff that I need to underline. It's not math, it's this statement. Conservation of momentum deals with the total momentum of a system, guys. The system is an isolated system. So a system is a system that only concerns itself with colliding particles. That's it. Action and reaction forces will become internal forces of that system. Internal forces do not cause acceleration. Internal forces of a system will always be action and reaction forces. Action and reaction forces will always be equal in magnitude and opposite in direction. So they will always cancel. So there will be no net force acting on these isolated systems. All right. System is not going to have a net force acting on it from outside. Forces generated during collisions will become internal forces. So they will cancel, which means that during impulse or during impact, during collisions, total momentum of a system before and after will be the same. Before a collision and after a collision, it's going to be the same. All right, so this is known as the conservation of momentum. So you're going to look at the momentum of a system before collision and after collision, before impact and after impact. You've got the before impact, so both masses may be moving. Take a look at the total momentum before impact. Take a look at the after total momentum after impact. All right, so total momentum before impact and after impact of a system is going to be constant. Okay, not individual masses. Total momentum of a system is going to remain constant, not the momentum of individual masses. All right, so this is the total momentum before, and this is the total momentum after. So they will be the same. It remains constant. All right, so let's add on to it. I want you guys to make the distinction. So what happens to the object's momentum if there's a net external force acting on it? Single mass's momentum. If there's a net force acting on that mass, what's going to happen is if there's a force acting on that mass for this duration, its momentum is going to change. Its motion is going to change. Its velocity is going to change. All right. So change of momentum in time is known as the force. So the force acting on a mass is going to change its momentum, which means that it's going to change its speed, its direction of that speed. It's going to change its velocity. It's going to cause it to accelerate. Originally, force was causing this mass to accelerate. That was the definition of it, which means that the force was causing the subject to speed up, slow down, and change direction. So that becomes the definition. Now it becomes force causing momentum to change. All right, so what force does, it changes the momentum of an object. All right, so this is the original way of looking at it. And with the impulse momentum theorem, it turns into this. And this is a much more powerful mathematical statement than this one is. Famous equation that Einstein came up with, E equals mc squared, came out of this equation, change of momentum in time. It's powerful. So what force does, acting on a mass, is going to cause it to accelerate. In essence, it's going to change its momentum. So what happens to the momentum of an object in the absence of a net external force? The absence of a net external force, nothing. Momentum doesn't change. There's no change of momentum. All right, so that's the same as Newton's first law. In the absence of an external force, the object at rest is going to remain at rest. The object in motion is going to keep on moving in a straight line at a constant speed. All right, so what's an isolated system? The isolated system is a system that only concerns itself with the colliding objects. That's it. All right, so in this case, it's going to be concerning itself with colliding objects, small mass and big mass. Action force is acting on one mass, the reaction force is acting on a different one. So that's an example of an isolated system. Head-on collision between a car and an SUV. Your isolated system is a car and an SUV. Person getting hit by a train. What's your isolated system? It's the person in the train. Tyson punching me in the face. What's an isolated system? Tyson and me. That's it. All right, so the isolated system is only going to deal with interacting objects. Colliding objects, interacting objects, that's it. Any two objects exchanging forces, it's an isolated system. Or any three objects, four objects, five objects. So the interacting objects usually form an isolated system. So what's the net external force between two colliding objects in an isolated system? Between two colliding objects, you will have action and reaction forces. And action and reaction forces will become the net force for the isolated system, which means that net force is going to be zero. So action and reaction forces will become internal forces. Internal forces don't cause acceleration. So which means the net force acting on the isolated system is going to be zero. All right, so we only have the internal forces. Internal forces don't cause acceleration. So what happens to total momentum between two colliding objects in the isolated system? Total momentum, not the individual momentum. So in the absence of an external force acting on the isolated system, there's no change of momentum. All right, so initial and final momentum of the isolated system is going to remain zero. Change of momentum is going to be zero, which means that the initial and the final momentum will be equal to each other.